Next, this is the most important property that we will look at in fluids. I've said that 3 times at least, but this one really is important. Viscosity. Viscosity is a quantitative measure of a fluid's resistance to flow. So you'll remember we talked about how a fluid cannot, unlike a solid, cannot deflect to offset a shear stress. It will deflect continuously, hence how a fluid can flow. However, not all fluids deflect the same under a given shear stress. That deflection is proportional to the viscosity of the fluid. As an example, here is you, and you are running, hair blowing in the wind, and playing soccer. Okay, now you've got air flowing around you. Air has a very low viscosity, which means it offers little resistance to an applied shear stress, causing it to flow, so you can move easily through air. Now imagine that you are playing soccer once again, but you are doing so in molasses. And here you are running. You're very sad because you're playing soccer in molasses. The good news is you will become extremely strong playing soccer in molasses, because the molasses is much harder to get to flow around your body. You must exert much more force in order to move just as fast as in air, because its viscosity is extremely high. In fact, molasses, so this is air and molasses, the viscosity of molasses, we use nu, is 65,000 times greater than the viscosity of air. So you'll have to exert 65,000 times as much force to move as fast. Good luck. Okay. Let's talk a lot more about viscosity. So one way to think of viscosity is as the friction between layers of fluid that are parallel to the shear stress. So let's say we've got this wall, and for now, let's say you've managed to stack a fluid into a cube. A block of fluid, we'll call it. Okay, now we're going to apply a shear stress to the top of this block of fluid. Now remember what we said. When a fluid experiences a shear stress, what does it do? It deforms, but unlike a solid, it deforms continuously. So we're going to draw this fluid after some period of time, and it is deformed some amount under an applied shear stress. Okay, now what we're going to do is we're going to look at, oh right, sorry, I meant to say the whole point of this was, again, think of it like there's just layers of fluid. And as this shear stress is applied and these layers of fluid are trying to move relative to each other, think of like a big stack of papers and you push along the top one somewhat hard and you drag all of them with you. Then this layer is going to drag this layer with it, which is going to drag this layer. But there is slip between the layers. This layer will be moving faster than this layer, which will be moving faster than this layer. And the rate of change of the velocity of those layers is actually how we're going to define the viscosity of a fluid. So let's again look at our wall. And instead of drawing it like this, I'm going to actually draw the velocity profile. Okay, so here is our y direction. Our x direction is equal to u, remember u is, if this is x and this is y, u is our x velocity, so the velocity of our fluid in the x direction, which in this case is the only direction the fluid is moving, so it's its total velocity. But the distance between the y-axis and this point represents the speed of the fluid. So you can see at the very bottom where it's touching the wall, the fluid is actually stuck to the wall because the adhesive force of the wall is stronger than the drag force, the cohesive force between the fluids. And so the fluid touching a wall will always experience the no-slip condition, which means that the velocity of that fluid matches the velocity of the wall. So the velocity of the fluid matches the velocity of the wall. All right. Now we can do a little bit of math. I don't know what to call it here, but we can define some differential changes, right? We can say there's a differential change in the velocity for a differential change in y. And you see here that the fluid speed, oh dear, close enough, the fluid speed is increasing. So the fluid speed is increasing as we move away from the wall. Right, we've got the shear stress being applied. And here, this fluid layer is stuck to the wall, and this shear stress is diffusing downwards through the different layers, such that this firstmost layer is moving slowly. This one moves a little faster, a little faster, a little faster, 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 faster. All right, so we can express this idea that the fluid is kind of rubbing against each other and its relative influence on the fluid with Newton's law. And Newton's law we're going to come back to all the time. I'd say it's one of the most important things we will write in this class, and it's how we define viscosity. So Newton's law is that the shear stress at any location y, so here's our shear stress, we'll say it's at location y naught, is going to be equal to mu, which remember is our viscosity, which is a quantitative measure of a fluid's resistance to flow. So here's our quantitative measure of the resistance to flow, and then that flow is equal to the rate of change of the velocity in the u direction as we go upwards in y at some given position y. Right? So du dy is just the rate of change, of the u velocity as we move in the y direction. So it would be equal to the slope of this line at a given point, say y naught. So you can see that this slope increases. So the rate of change, remember it looks like the slope is smaller, but it's the rate of change. So du dy it's getting much faster. Here it's 0, here it's going fairly fast. Whereas the closer we get to the free stream, it is called, then you see our u isn't changing very much for the same distance dy. So here we saw a large change in u for dy. Here we saw a small change in u for dy. And so Newton's law just tells us that the shear stress in the fluid is proportional to the rate of change of the u velocity in the y direction multiplied by a constant, the viscosity. Okay, we're going to spend a lot of time on this throughout this class. Something we should talk about is what are the units? Okay, so this is a shear stress, so it should have units of pascals, right? So then, what do the units of viscosity need to be? Since here, we know that u is a velocity, right? The velocity in the x direction, and y is a length, right? A distance, so meters. And so we see that this would leave us with our unknown value times 1/seconds. And we need to have pascals. So if we solve for question mark, we find that question mark is equal to Pascal seconds. So viscosity has units of Pascal seconds. Also, viscosity is highly influenced by temperature. So we should use temperature dependent properties whenever we can. Okay, let's talk a little bit more about viscosity. Specifically, it's not always as simple as Newton's law. Right, so Newton's law was nice. It said that the rate of change of the fluid's velocity in the y direction is proportional to the shear stress by a constant. However, that's not always true. Sometimes you have non-Newtonian fluids that don't follow Newton's law. Okay, what that will look like instead is, let's draw a plot. Here's the shear stress. Here's du dy. Okay, so remember, du dy and shear stress with Newton's law are related by a constant. So that means that for Newton's law, you would have a straight line relating those two things together. This is Newtonian, which is linear, and the slope of that line would be just the viscosity. But there are some fluids that don't follow this behavior. There are some where these are called dilettantes, or we call it shear thickening. So essentially, as the flow increases, as we're moving faster and faster, then the amount of shear stress you need in order to achieve that flow increases with time. With flow speed. Likewise, we have the opposite, a pseudoplastic, which we will call shear thinning. Okay, and this is the opposite, where as our speed increases, or the rate of change of our velocity in the y direction, then our shear stress actually doesn't increase in a linear fashion, but kind of dies off. So this kind of results in some pretty cool behavior, and we're going to watch some pretty cool videos. Let's go here first. Okay, so let's talk about shear thickening. Okay, remember, shear thickening was right here. So what this really means is our fluid becomes, we could call it stiffer or thicker, or what I might say is more like a solid, right? The larger kind of the required du dy per unit shear stress, or vice versa. In other words, the higher the viscosity, then the closer you get to a solid, right? Going back, air is nice. Molasses is closer to like moving in a solid. So the higher your viscosity, the more like you are moving like through a solid. Okay, so shear thickening is fluid is becoming stiffer or thicker more like a solid as the strain rate increases. And it's doing it at a more rapid rate than a Newtonian fluid does. So the best example of this, which you've probably played with, is oobleck, or cornstarch in water. Okay, another example is quicksand. So quicksand, right? Here's our quicksand. There's a person and they walk on the quicksand. If they hold still, in other words, there's not a lot of shear stress on the fluid, then the fluid becomes less viscous, more like water or air, and the person begins to sink. And they say, ah! And they say, well, this should be easy to get out if I sunk right in. But as they start thrashing their arms around, as they start saying, get me out of here, and they're moving their arms around, and they're causing shear stress in the fluid, the viscosity is going up, and so it becomes closer to molasses. And so you sunk easily because when there was no shear stress, it had a low viscosity like water. But if you start to induce shear stress by thrashing around, the viscosity goes up, and it's now like molasses, which is why if you want to get out of quicksand, you must move very slowly to reduce the shear stress.